This, you're right, the title is too long. Sorry about that. And this will be a distraction. Majority of topics of today, I noticed it might be considered a breach in terms of pressures involved, because in the morning we listened about megapascals, tens of megapascals. Right now we listened about 0.5 kilopascals. So here we will be talking about single kilopascals. And so nanopores, just to set it, to put it in context, no condensation, no interfaces, no menisci. The nanopores are completely wet in this case, and this is about ions which are there. So what happens to these ions if we apply pressure difference to a nanoporous material? So this kind of topics was touched upon yesterday by Benjamin Rothenberg. It's a pity that he is not here, but okay. I understand this has been recorded, so at least he will be able to see. So basically, this is the outline. So as I mentioned, this will be about nanopores and electrolyte solutions. And in fact, in this case, there are several phenomena that are being gradually adopted, so to say, by the community. Also, many of them were known before in colloid science, but people rediscovered them maybe in nano-engineered systems with well-defined geometries. And these are surface conductance, streaming current, and streaming potential. And I will be talking more or less about this kind of phenomena, which are related to the fact that once a surface is in contact with water, typically there is some charge separation. The mechanisms may be various, so it might be preferential adsorption of either anions or cations, more frequently anions. It might be dissociation of the so-called ionogenic groups, which means in a dry state it's a neutral, and then in water, hydrogen, for example, splits off, and there is a negative charge remaining. But what is important to realize, typically, this kind of surfaces are referred to as charged, but basically, no, they are not charged. The system remains neutral. There is a charge separation. So, but what is important is that a part of this charge is somehow bound to the surface, so chemically, and another part, compensating charge, is mobile. So this gives rise to interesting phenomena. Okay, so then I will explain a little bit the physics of this, and then I will demonstrate that actually interplay between two of these phenomena, which are streaming current and surface conductance, give rise to non-monotone dependencies of streaming potential on surface charge density with some maximum magnitudes. What happens is that in experiments, people observe larger magnitudes. And then, well, the question is, well, essentially larger. So maybe several times larger. And even in this talk, I will show you some examples how by interpreting results in an incorrect way, you can also conclude, yeah, we have something which is much larger than the theoretical maximum. But of course, if you don't understand the subtleties, you can also start shaking the foundations of the universe and say, no, it's just the model doesn't work. Fundamentally, there is a slip or whatever. Well, I'm not saying there is no slip, but here we can explain the results in a more conventional way, but we need to take into account some phenomena which we see in time-resolved measurements. And they are, you will see, very simple. So extremely simple measurements to do. So at least for this kind of materials, the conclusion will be that this second explanation in terms of ion rejection by nanopores is more plausible. Okay, so now to streaming current. So as I mentioned, you have these negative charges on the surface. I'm not sure you can see them, these small minuses. So they are somehow chemically bound to the surface, so they cannot move. And you have those pluses which are in the solution. So they are in thermal movements. They are called counterions. So now imagine what happens if you apply pressure difference and the liquid starts moving. Okay, you will have here inside this capillary convective current. So you will have a movement of charged liquid. Remember that the negative charges don't move. The positive charges are entrained by the flow. So you have convective current. And if you have right outside electrodes, which, how to say, produce and absorb current immediately at the entrance and at the exit, so to say, you will have current, streaming current conditions. By definition, streaming current occurs at zero potential difference. This is important to realize. So streaming current is non-potential phenomenon. So you cannot apply Ohm's law to it, or Kirchhoff's or whatever, which states that to have current, you need the potential difference. Here, you have current at zero potential difference. But this picture also tries to illustrate some difficulties with the measurement of streaming current. So I'm not sure you can see this small print, but basically, if your electrodes are not immediately close to the surface of the material, then you have some ohmic drops. And then you also have some overvoltages on the electrodes, which must be reversible, but in many cases, they are not fully reversible in real experiments. So in summary, measuring streaming current is difficult, technically. It depends. So if you have a thick diaphragm, something like that, maybe you can do it, but typically people opt for a simple thing, which is called streaming potential. And in this case, the external circuit is open. And what happens is shown here schematically. So you have zero current, of course, but you can imagine this as two components which compensate each other exactly. So you still have streaming current from left to right, and then you have conduction or electromigration current from right to left. And physically, this happens because here at this edge, you have some excess of positive charges, which leave the system just at the distance about screening lengths. On the other side, you have deficit of positive or negative charge. And you have a plane capacitor, so to say, an electric field, which creates conventional current, which compensates streaming current. And in this case, the measurement is much easier because you can position your electrodes anywhere outside. There is no current outside the system, so no ohmic drops, nothing. No currents, so reversible electrodes will be reversible. So very simple, but there is a snag, which is that, okay, this the magnitude of this conduction current is controlled by the conductivity of the liquid. If the pore is large, this is the conductivity of bulk solution. And this gives rise to famous in our communities formula, which dates back by more than 100 years, which shows here the so-called zeta potential, viscosity, lambda is solution conductivity. And as long as the pore is large, it's bulk conductivity. But when the pore becomes a real nanopore, then these charges, compensating fixed charges, take up ever larger volume of the pore, and then the conductivity is increased. And this is called surface conductance, this phenomenon. And I think it's not so difficult to understand that, okay, if you increase the surface charge density, then both the streaming current and surface conductance increase, because you have more charges that move, but due to this parabolic velocity profile, you increase the charge, the volume charge density more at the surface. And that's why the increase of the streaming current is slower than increase of the surface conductance. And basically, this gives rise to a dependence with the maximum I have already spoken about. And the problem is that, what you do if in experiments you measure a larger magnitude. So what could it be? And then, as I mentioned, you have this simple formula, which is basically accurate in semi-quantitative terms. So we see that here we have, for example, viscosity in the denominator, and then postulating that there is some slip at the surface is roughly equivalent to assumption that viscosity is reduced. So of course, if you reduce the denominator, you increase the quotient. Yes, you can explain this in this way, in larger magnitudes. But if you do time-resolved measurements, you see that the situation is time-dependent and so on and so on. And then this is a scheme of extremely simple experiment. So you just have a cell, you have a level. It even doesn't need to be very high. So you don't need stairs or whatever. It's typically maximum of 1-2 meters. And that's it. So you have a valve, you open the valve, you increase the pressure. Fortunately, the processes are not so fast. So we don't, in this case, we don't need to increase pressure in milliseconds. So it's enough to do it in 1 second, maybe. And then we have time evolution. And now I will show you some pictures of the membrane we have used, one of two kinds. So these are, the first one was the so-called track-edged membrane. You can see here the thing. There are various samples, taken from a review on that. I think you can see cylindrical pores, which are more or less parallel. In this case, there are also other varieties where they, how they are obtained. First, they irradiate polymer film with heavy ions, and after that they etch the tracks. And then this irradiation can be like this, a collimated source where you have only parallel tracks, or sometimes they do deliberately irradiate with varying angle in an attempt to increase the porosity, because in this case, the pores do not overlap over the whole length. So if they are parallel, then there is a probability that they will overlap. They typically want narrow pore size distribution. So trying to avoid this complete overlap along the whole length, they use this crossed pore. But this does not change in principle the fact that the pores are straight and cylindrical. So this influences only the effective length of the pores. So basically, this is just short information on the membranes we have used. And these are some experimental data plotted here as a function of square root of time. So now we are coming to diffusion again. So, and okay, to the right are experimental data. Okay, these are averages of typically 5, 6, 7 measurements. I don't show here the error bars because they are pretty small. So they would obstruct the view because the lines actually are theoretical fits. So they are not guide for the eyes, they are theoretical fits. And if I would put the error bars here, they would obscure, you would not see the theoretical line. It would be hidden. So they are pretty small. So the agreement is very, very, very good. Typically, what else can we say? You can see that these initial ones are linear. So one can define the slope of this initial part. But in our context, what is important is that the true streaming potential is this, not this. And just look at these plots. For example, for this curve, we have below 2 millivolts at the beginning and more than 4. And even this is not the end. Actually, the evolution continues. So we have several times difference between this initial value, which is a true streaming potential, and then something like that can be taken as a steady state. So I would say if people don't understand the physics I'm going to explain right now, they can say, okay, there are some transient phenomena, we don't really know what it is, but let's wait until steady state. So if they do this, of course, they will use these values. And here on the left, I have shown some calculations of dependence of streaming potential coefficient on the surface charge density. And the dotted lines are experimental values for one of this series of methods. So what we see, so we can find the surface charge density corresponding to experiment. But now you see that the maximum is just 30% above this value, something like that. But these values are much more than 30% above. So if you would use these values, you would not be able to determine the surface charge density because your measured value would be above the theoretical maximum. Of course, yes, you can start speculating and saying, well, actually, this model is not applicable. So we have used really conventional model, Poisson-Boltzmann equation, charged liquid, the electric continuum, all this, but full version without any simplifications numerically. But yeah, if you say, okay, viscosity is reduced, then you can get anything you want. But then this time dependence, for example. Right now, I'm going to explain where does it come from. And we have, as you see, an excellent agreement with the model. So, next. Just equations crammed in one slide. The basic message is that this is just a non-stationary diffusion equation. The physics is that this kind of nanopores, charged nanopores, they reject ions, which means that if you push dilute electrolyte solution through such pores, due to electrostatic interactions, ions stay behind. Some of them pass, but there is what is called rejection. And this creates this situation shown schematically on the right. So there are concentration profiles arising in the system. Due to the fact that the so-called electrochemical selectivity of the membrane is different from the electrolyte solution, this gives rise to some voltages. And these voltages occur on top of streaming potential. So initially you have just streaming potential without any concentration gradients, and then you have the buildup of these concentration gradients and the corresponding voltages. And as we have seen, these voltages, for example, here we studied nanopores of 25, 35 meters in electrolyte solutions of 1 and 2 millimoles. So in this case, this additional voltage is several times larger than the initial streaming potential. So it's a major contribution. If you go to even smaller pores, for example, it gets even worse. So, so I would say many people would call this streaming potential, but this is not streaming potential. So this is mostly diffusion potential caused by ion rejection. And this is what we see in this time of salt measurements. Well, there are several checks. To say, for example, we apply very low pressures. So the thing should be linear in pressure. And then indeed we see, so I'm not going into details, but you see, I think, these linear dependencies. Okay, and then, well, there are some other details, but I would say it's pretty certain that this works. Now, you know, just some numbers. The surface charge densities we obtain from heating. Also, in my opinion, quite reasonable. Not really hundreds of millicoulombs per square meter. So that's why I am surprised when I see this kind of numbers. So typical values, I think, are around 10 millicoulombs per square meter. And well, okay, I have still a couple of minutes. And I would like to show you that actually this is not specific for the membrane we discussed previously. So this is another membrane which has a pretty different structure. In fact, it's a commercial product which is obtained in this funny way. So they mix a polymer precursor with the silicon nanoparticles. I don't know how that they do this, but they achieve very homogeneous structure with very high volume fraction of nanoparticles, and then they polymerize and they etch out the silicon. And they obtain this kind of structure with funny pore structure like nanocavities connected with bottlenecks, something like that. But these bottlenecks may be like 20 nanometers, the cavities are like 100. We cannot describe this mechanistically like the track edge membranes. No, we did not do this, but we did the measurements. So this, by the way, are some examples of real measurements as a function of real time. It's not square root. So this is, I think, illustrates what I mentioned. So this can be easily taken for students. It seems to be approaching, but the real value is somewhere here of streaming potential. And you need to treat this data to extract it. So this is just dependence on pressure because we need also the hydraulic permeability for the interpretation, but this is very simple measurement again. Well, these are some examples now with error bars. So you see in very dilute solution, of course, with much less scattering because the signal is larger, is magnitude. Well, and these are fits. Okay, I don't know if you can see. Blue are experimental data, averaged over 6 to 7 measurements, and red are theoretical fits. So the quality is extremely high. What else? It's just comparison of two different concentrations to show that indeed in dilute solutions, this difference between initial and steady state value becomes much larger. What else? These are fitted parameters. This probably is not that important. So, no conclusions. So basically, I think the principal conclusion is that the pressure-induced electrical response to pressure in nanopores is actually dominated often not by streaming potential, but by concentration or diffusion potential. And this is seen in time-resolved measurements, which are not terribly complicated, but you need to know that they are needed. So to interpret results in a correct way. So we have demonstrated this for two kinds of membranes, straight-edged with cylindrical pores, and also other membranes. Well, this is very recent, so we did not have time yet to do mechanistic interpretation, but this is on the way. So maybe next time I will be able to tell you about this membrane, which actually is very interesting material in terms of practical application, extremely stable, polyimide, stable up to 200 centigrades, organic solvents, acids, bases, so extremely interesting material. So yeah, that's it. So acknowledgement and didn't I have thank you for your attention? No, sorry, but I tell you this. Okay. Thank you.
Thank you, Andrew. So a couple of questions.
I was wondering, when you study your transient regime of the streaming potential, do you take into, so you build the difference of concentration between entry and exit? Do you take into account diffuse osmosis that would arise because of this?
Diffuse osmosis, you mean? A good question. I would call it just osmosis. Why diffuse osmosis? I don't know. It's just osmosis.
Diffuse osmosis because you would have an impact on the flow of liquid that is needed to build the difference of potential. So this is the reason why.
No, well, this is taken into account. In fact, there are two varieties of interpretation, but in general, keep in mind that all these phenomena are pretty small. Given that we are applying pressures like 2 kilopascals, the concentration changes are 5%, maybe 10% as a maximum. So this is across the membrane.
I mean, but if you don't have any change in concentration, why would you have a change in potential?
Yes, we do, but it is proportional to this relatively. We are measuring millivolts. And it is proportional to this relatively small difference of concentrations. No, but just briefly, we do take into account osmosis. Osmosis brings about some decrease in the flow. So we apply constant pressure difference, but the flow actually changes with time due to the build-up of osmotic. But this is not the big phenomenon. And we have a routine for solving the complete set of equations. And we have an analytical solution which gives us 10% accuracy, more or less, which neglects all this complicated phenomena. But we can discuss it if you want.
Sure. Very, very quick one.
Yes, so analytically, you have some transient analytical solution. Where does it come from?
Well, we have this non-stationary diffusion. So it's just Fourier transform. It comes from Fourier transform. So we solve a very simple equation for the Fourier image of the function. I don't know.
No, it's hydrodynamics behind.
No.
The time dependence.
No, well, hydrodynamics, yes, but you postulate that you have some flow, right? Externally induced, and then there is some ion rejection at the interface with a certain coefficient, and this gives rise to some concentration changes in the solution outside of the membrane. So there you have equations which you solve. Non-stationary convection diffusion. Generally, it's a non-stationary convection diffusion equation, but at low flows, you can neglect in the first approximation some nonlinear terms proportional to the Becquerel number squared, for example. So you do a linear analysis, and in this case, you can make Fourier transform, not generally, but numerical solution is also simple. So fully numerical, just without neglecting anything.
Thank you again, Andrew. So the next talk is from Gonzalo Paula. I really don't know the title of the talk. It's not in the programs. Yeah, so.